So we talk about the strength of an electrolyte. Remember, strong electrolytes and weak electrolytes. And the strength depends on how far the dissociation into ions goes. So a strong electrolyte will dissociate completely, like sodium chloride. You dissolve that in water, all the sodium ions go off by themselves, independently, all the chloride ions. You don't see any NaCl molecules floating around. Whereas a weak electrolyte only partially dissociates. And, no, I don't want to go there. So we use the same idea for talking about the strength of an acid. So an acid reacting with water will form hydronium ion, which is essentially hydrogen ion, right? It's donating a proton to the water, and A minus. So this is the conjugate base of this acid. If this equilibrium goes all the way to the right, then it's a strong acid. It reacts completely. If it's a weak acid, it only partially ionizes. And so then this equilibrium is going to be, somewhere in the middle. And you're going to have HA present, and you're also going to have A minus present. So this is an equilibrium, and this is why we talked about equilibria before we talked about acids and bases. So there are 6 important strong acids. Memorize them. There's only 6. If it's not one of the 6, I expect you to tell me it's a weak acid. Okay, so there's 6 strong acids, and these are hydrochloric, hydrobromic, and hydroiodic acid, and those are 3 of the halogens, right? HCl, HBr, HI. And then nitric acid, perchloric acid, and sulfuric acid. These are common acids, so they're very familiar, but you just have to remember which ones. So we can talk about acids as being monoprotic, diprotic, or triprotic. So protic refers to proton, and the prefix in front tells us how many of those ionizable protons there are. So a monoprotic acid has just one hydrogen. So these guys, most of them are monoprotic acids. They can only donate one hydrogen ion. A diprotic acid has 2 hydrogen ions. So this is the parent holding 2 babies. And I can pass off one to the babysitter. I can pass off both of them to the babysitter. I could give one to that babysitter and one to another babysitter, right? Sulfuric acid is a diprotic acid, H2. Now, if you have tried to look up names and formulas of things on the internet, you may have found some different orders of letters, right? This is the way we write the formulas for acids in general chemistry. In general chemistry, the hydrogen comes first, and those are the ionizable hydrogens. If there are any other hydrogens, those are later on in the formula. Organic chemists write things a little bit differently because they're focused on something else. And then, other disciplines have their own way of writing the formulas. A triprotic acid is going to have 3. Anybody think of a triprotic acid? What's H3 something? H3PO4. Phosphoric acid would have 3. Most of the acids we're going to see are monoprotic. So, strong acids. HCl is a strong acid. When we dissolve this, it ionizes completely. And notice we say contains virtually no intact HCl molecules. I like this because we're starting to not lie to you so much. When we say this ionizes completely, does that mean there's not even one HCl in there? No, there could be. But the number of them is so insignificant that we can ignore them, right? So it essentially ionizes completely, so we just say it ionizes completely. When we write the chemical reaction for HCl with H2O, we use a single arrow. The single arrow indicates that this reaction goes in the forward direction to completion, doesn't go backwards, okay? So if we have a 1 molar HCl solution, remember that capital M is moles per liter, so this is 1 mole of HCl per liter, then what's the concentration of the hydronium ion? Well, for every 1 mole of this, we have 1 mole of that. So the concentration of hydronium ion is the same as the concentration of the acid. We also have 1 molar chloride ion. We didn't look too much at concentrations of individual ions in Chem 1A. We did a little tiny bit. And we're going to do that a lot more here because we have a lot of reactions that occur in aqueous solution. And we're interested in the hydronium ion concentration here. The chloride ion concentration doesn't matter to us at all because that's going to end up being a spectator ion. So we mentioned hydrochloric, hydrobromic, hydroiodic. At the top of that column is fluorine. HF is also an acid. It's hydrofluoric acid. Is HF a strong acid? No. So the thing I think about here is I think of the halogens as being sisters. Fluorine, bromine, chlorine, and iodine. They form polyatomic ions with oxygen in the same way. They're not the same, but they have similar characteristics. Well, who's the smallest? Fluorine. So the smallest one of those is weak, the others are strong. The size does not correlate to Y, but if it helps you remember. So HF, fluorine is the baby sister there, and so HF is a weak acid. So when we write an equation describing how HF reacts with water, then we have equilibrium arrows. This is going both ways, and it's not complete. So some of the HF will donate a hydrogen to water, making hydronium ion and a fluoride ion, but a lot of it won't. So here we have a picture with letters and here with models. So here's the HF, and some of it ionizes, but some of it does not. And so we still have these intact HF molecules floating around. If we want to know the hydronium ion concentration in a 1 molar HF solution, without any other information, all we can say is that it's a lot less than 1 molar. Yeah?
The reason why it's a weak acid is because of fluorine's ionization energy?
Yeah. Fluorine, well, not its ionization energy, it's electronegativity. So fluorine is extremely electronegative, and so it holds on to that hydrogen ion very tightly, and so it does not like to let go. So that doesn't work with strong, weak, so I don't usually talk about that. If we dissolve 1 mole per liter of HF, we're going to get less than 1 mole per liter of H3O+. So the acid strength depends on the attraction between the conjugate base and the hydrogen ion. So with a strong acid, the interaction, and this kind of gets into what I just talked about, the hydrogen ion and the conjugate base are attracted to each other, but weakly, very weakly. It's a weak attraction. Because that's a weak attraction, it's a strong acid. So I'm sorry if the opposite strong-weak thing is confusing. I think it's confusing too. In a weak acid, the attraction between the hydrogen ion and the conjugate base is stronger. So fluoride, being more electronegative, is going to have, and small, is going to have a more strong attraction to the hydrogen ion. So some of it will give up its hydrogen ion, but not all of it. This is the acid, that's the conjugate base. If the acid is strong, then the conjugate base is weak. The stronger the acid, the weaker the conjugate base. Well, how do we know where that equilibrium lies? An equilibrium constant. So here we're calling this equilibrium constant Ka, because it's the constant for the ionization reaction of a weak acid. And it's called the acid ionization constant. So if we look at this acid interacting with water, it forms H3O plus and this conjugate base, A minus. So we can write an equilibrium constant expression for that. It's the concentrations of the products divided by the concentrations of the reactants. Why is water not in there? It's a liquid and its concentration doesn't change. So we don't include liquids or solids in equilibrium constant expressions. We can also write the same equation in a simpler form where we're just focusing on that hydrogen ion and we're kind of ignoring the fact that water is there holding the hydrogen ion. So this acid ionizes into H plus and A minus. So using this equation, we get H plus times A minus over HA. H3O plus and H plus are interchangeable. The only difference is that here we're acknowledging the fact that the hydrogen ion is being held by a water molecule, and here we're ignoring the water molecule. It's there. This is aqueous. We know that's what it's doing, but the equation gets a little simpler if we ignore that. So if we have a small ionization constant, that means it does not go very far to the right. So that means we have a weak acid. A strong acid would have a very high ionization constant and would go all the way to the right. So Ka is a measure of the strength of an acid. Any questions? So this is a table from the textbook showing some acids and their ionization constants. This is not something you memorize. I do not have memorized any of the Ka or pKa values for weak acids. We just look these things up. There's always the students that don't want to memorize the important things, like the 6 strong acids. Remember, I flat out told you, you have to memorize the 6 strong acids. And then there are other students that are going to text me and say, well, do I need to memorize the Ka for formic acid? No, you don't. We look them up. So here we have the names of the acids, their formulas, their structural formulas, right? Benzoic acid is really kind of fancy here. It's a little bit like phenol. And we have the ionization reactions where we see how they are interacting with water and what the conjugate base is. This is the ionization constant, the equilibrium constant, and this is pKa, and we'll talk about that in a minute. So there will be homework questions where they do not give you the Ka value. You have to go look it up. When the questions are in a computer interface and it's going to tell you whether it's right or wrong, it's a good idea to choose the value of Ka that the computer is most likely using. And so look in your textbook for homework problems, right? Are these exact numbers? No. Here, they've just got two significant figures. These are at 25 degrees Celsius. Do equilibrium constants change at different temperatures? Yeah, they do. So you look something up, and you may have accidentally gotten something for 20 degrees or some other number, right? So use your book. Okay, magnitude of acid ionization constant. So here we've got three generic weak acids, and the images are showing how they're ionized at room temperature. Which acid has the largest Ka? Well, let's think about, what does a large Ka mean? It tells us about the balance of the equilibrium, right? Is it going to favor the products or the reactants? High Ka favors the products. So here, larger Ka, we're looking for the one that has more products, right? When an acid ionizes, it forms a hydrogen ion and a conjugate base. So which of these has more hydrogen ions? B. So this has one hydrogen ion, this one has 4, and that one has 2. These are weak acids. If one of them was a strong acid, we would see none of the white and green together, they would all be separate. Consider these two acids and their Ka values. Which acid is stronger? Strong acids dissociate completely, so their Kas are going to be larger or smaller? Larger. Large Ka, stronger acid. So we're looking for the stronger acid. We need to identify which of these numbers is larger. A. And this is where negatives can kind of mess with us, especially, if you're just trying to do it quickly. This is -4, that's -8. Your brain says 8's bigger than 4, but this is negative, which means we move the decimal point further away and this gets smaller. So just watch out for that with the negative exponents. They're always going to be negative exponents.